some polynomial theorems that come in very useful. The first one's our remainder theorem, which certainly can save a lot of time. If all we're interested in is the remainder, not having to do the huge long division is useful. And all we have to do, if we're dividing by a linear factor, is substitute in a, and that'll get us the remainder every time. So the proof of that, okay, we know that polynomial x can be written as divisor times quotient plus the remainder. Now, let's say the divisor is x minus a. So just substitute in. Well, polynomial a will become a minus a, which of course is 0, plus remainder a. However, what we know is that the degree of the remainder is going to be less than the degree of the divisor. Now, the degree of the divisor is 1. Therefore, there's only one possibility for the degree of the remainder, which is 0. If the degree is 0, then it must be a constant number. So it doesn't matter what I substitute in. So therefore, remainder x is the same as remainder a, and that will equal polynomial a, as we see up here. So there's our little proof. So using that, well, as I say, there's the division that we did yesterday. I think it's the same one. But instead of having to do the whole division, all I've got to do is substitute in 2. And we come up with the answer that we came up with yesterday of negative 19. Heck of a lot quicker. Having a theorem which involves linear factors is very useful, especially when we now turn it into the factor theorem. If it is a factor, then what would the remainder be? Right, there'd be no remainder. So the factor theorem is really the remainder theorem, but what we're saying is the remainder would be 0. So if we substitute in a, we get an answer of 0. We know it's a factor. Now, as I was just saying, all polynomials can be reduced down to linear and quadratic factors, but once we start learning about complex numbers, all quadratic factors can be broken down to linear factors. So it can be just a series of linear factors. Using this theorem, it can find those linear factors for us. Right, they've given us a bit of a hint here. They've told us x minus 2 is a factor of this one. Hence, go and factorise the polynomial itself. Well, now I know my factor theorem. I can substitute in 2. Sure enough, it's 0. So that shows it is a factor. It then says factorise. Now, this is where it's a bit silly using the factor theorem if you think about it. Because now to find the other factors, I have to do a polynomial division. And when I do my polynomial division, so x cubed divided by x, x squared, multiply out, subtract, we can keep going, multiply out, subtract, we can keep going, and there's our remainder of 0. So why did I bother with the factor theorem when over here I had to get that remainder of 0 anyway to find the other factor? And I guess the reason is, most of the times, we don't use polynomial division to find the other factor. We use a little bit of logic. Let's complete our factorisation. So x squared plus 2x minus 15, and x squared plus 2x minus 15 also factorises. But here's how I would have done that question. So I would have used the factor theorem, confirmed x minus 2 is a factor. I'm going to say, well, it's x minus 2 times what? But let's look at particular terms. And I know the leading term times the leading term must give me the leading term. So to start off with, let's look at that leading term. X times what gives me x cubed? Well, I know the other one, therefore, must start with x squared. Then I do a similar thing with the constant. Constant times the constant must give me the constant. So negative 2 times something will give me 30, with negative 2 times negative 15. I just need to find the middle term now. Alright, well, how many x's? If I was to just leave it like that, how many x's would I have? Right, there's only actually one expression that will give it, and that would be the minus 15 times the x. That's the only thing in that would produce a term with x. I don't want minus 15x, I want minus 19x. So how do I get from minus 15 to minus 19? So therefore, negative 2 times our missing term must give me negative 4x. Alright, so that process, if you were to expand out now, how many x would I have? Well, our answer was we'd have minus 15. How many do I need? Well, I need minus 19. Well, how do I get from what I have to what I need? Minus 4x. So I'm saying, well, minus 4x then must be negative 2 times the missing term that I want. So that missing term must be plus 2x. I could have done it using x squared rather than the x's. So if I was to look at it, remember the missing term's missing, hence the name missing term, we got minus 2x squared. But I want no x squared. Therefore, to get from minus 2x squared to x squared, I'd have to add 2x squared. So it would be x times plus 2x would give us the 2x squared. And so we end up with our other factor, and we can factorise it again. Well, this second one, they haven't given me any hints. So I'm going to have to use the factor theorem to work out the factors. Now, yeah, if I was to just randomly to pick a number, I could be going forever. So I need to use a little bit of logic. The number that I'm going to factorise in will be the constant in the factor. And we know the constant times the constant will give the constant. So I know, therefore, it must be a factor of 36. Okay? So constant factors must be a factor of the constant. I get one or two possibilities. I purposely picked a number there that has quite a few factors. So there's still a few to choose from. 1, 2, 3, 4, 6, 9, 12, 18 and 36. Of course, who's to say they're positive? Could be a negative number as well. And that's terrific if it's monic. This one's not monic, you'll notice. It's 4x cubed. So we might actually have a fractional factor. We might get an answer of x equals a quarter or something like that. So how do I work out the fractional factors? It'll always be factors of the constant, which we've worked out, over factors of the leading coefficient. In this case, 4. So I could divide them all by 4 and their possibilities. Some of those we have already, of course. 4 over 4 is 1, for instance. So I can cross those out. I could have them over 2. 2 is a factor of 4 as well. Again, some of those are repeated. I don't need to try those. Okay. Of course, they could be negative as well. So we have several numbers to choose. Which one would you pick first? Yeah, 1's probably the easiest one to try and hope for the best that 1's a factor. You can get it in there. So logically, I went for 4. Wow. Oh, look, it worked. Oh, sensational. How good was that? Yeah, I probably did go 1 first and then try that. But, so all right, I know x minus 4 is a factor. Okay, let's try and work out the other factor. Leading coefficient times leading coefficient. So x times something gives me 4x cubed. That's going to be 4x squared. Negative 4 times something gives me 36. That's going to be negative 9. What's the missing term? Now I can do it using the x squareds. I can do it using the x's. It doesn't really matter. Which one shall I use? So we have choice. Isn't this great? You know. At this stage, if I was to expand out, I would have minus 16x squared. We have minus 16x squared. We're done. There is no middle term for this one. Now, if you don't believe me, let's check the x's as well. At this stage, we have minus 9x. Minus 9x is what we want. So in fact, that second factor there is 4x squared minus 9, which does factorise to be 2x plus 3 2x minus 3. So the other two factors, hey, lucky I hit on 4 straight away, hey, because the other two factors would have been negative 3 on 2 and positive 3 on 2. Let's have a look at an old HSC question. So they've given us a polynomial. We've got a quotient with a divisor. The remainder, well, it's a linear function, the remainder, but they've written it as, instead of ax plus b, they've written it as ax plus 1 plus b. Oh, possibly, so there's a common factor there, but alright. If I'd read the next line, it would have made sense. When polynomial x is divided by x plus 1, the remainder is negative 11. And when it's divided by negative x minus 3, the remainder is 1. What is the value of b? Okay. Polynomial negative 1 is negative 11. B is negative 11. Because this first expression will become a 0. The second one will become a 0 as well. And we're just left with b. So b is negative 11. So what is the remainder? Well, now we've got to find a. Well, there's the other piece of information they've given me. Divided by x minus 3, the remainder is 1. So I know polynomial 3 is 1. Substitute that in, the first expression becomes 0, so that's fine. But the next bit, we get 4a plus b is equal to 1. We've just worked out b is negative 11. So we end up with a is 3. The remainder is a x plus 1 plus b. So that's 3x minus 8. So this time, we've got x plus 2. The remainder is just a constant in this case, it's plus 3. Find the value of a. Well, we can substitute in any number we like into this, but there would be a smart one to substitute in, because of course we don't know what qx is. So the one to substitute in would be to make that equal to 0, so that qx disappears. So polynomial negative 2 is equal to 3. Subbing in, and eventually, there it is, a is 19. Okay. Oh, that's all there was to that question that year. Oh. 94. This time we're divided by a quadratic, x plus 1, x minus 4. Quotients qx, remainders rx. Okay. One of those questions you love where you actually have to explain rather than just answer the question. Y is the most general form of Rx given by Ax plus B. Well, that's using the idea of the degree of the remainder must be less than the degree of the divisor. Now, the degree of the divisor in this case, we said it was a quadratic, so therefore, at most, we could have a degree of 1. In other words, a linear function. Well, it might turn out that it's a constant number. Like a might have turned out to be 0. But we're saying, at most, what could it be? It is possible it could be a linear function. Right, we're now told that when we sub in 4, we get negative 5. Show that remainder 4 is negative 5. Hang on. Let's write our polynomial down. So it's x plus 1, x minus 4, qx, plus remainder x. So subbing in 4, the first expression disappears. I'm left with the remainder 4. We got the answer straight away because they've told me polynomial 4 is negative 5. Further, when we divide by x plus 1, the remainder is 5. Now we've got to find that ax plus b. Righto. We know remainder 4 is negative 5. But so 4a plus b is negative 5. But we now know polynomial negative 1 is positive 5. So minus a plus b is 5. Simultaneous equations. Where a is negative 2. B is 3. So my remainder was ax plus b, so minus 2x plus 3. That type of question, where they divide by this quadratic and do work out the remainder, gosh, it crops up a lot. I've seen it in so many different papers, both trials and the actual HSC itself. Okay, so 4D, I've just made a little note here. If the factor's 2x minus 1, then the number we would substitute in it would be a half. Basically, you're saying what makes the factor equal to 0. So it would be x equals half would make that equal to 0. That's how you can find that particular factor.